Hey guys, welcome to Biophysics Class 35. This is on the action potential part 2, and in this lecture we'll learn about how the ion channels are gated with voltage, which allows for the control and the movement of ions into the cell membrane, into the axon membrane, and out of the axon membrane. And we'll also look at how we can build a circuit model of the cell membrane, anticipating our Hodgkin-Huxley model, which will be our culminating model of the semester. So um, we start off by looking at what's called voltage gating of the sodium channel, and it involves something called activation and inactivation. So let me explain what those terms mean. So first of all, remember that the action potential looks like this. We have the membrane potential at a negative value, and then a stimulus, which causes the um, sodium current to flow in, increasing the membrane potential with the positive ions coming into the axon. And then eventually, in some way, the sodium stops entering and, oops, and the potassium leaves, okay? And when the potassium leaves, that brings, since positive ions are leaving the interior, that brings the membrane potential back to um, its resting potential of -70. So let's take a look at this in more detail. This is a picture of a sodium channel through which the sodium ions move. And there are actually two types of gates. There's an activation gate, which is the main gate in the center here. And then there's an inactivation gate, which is this little gate here, and this little ball can move and close there. Okay, and both gates are necessary for the sodium to do what it needs to for the action potential to occur. So let's look at how that might work. So at position 1 here, we have the activation gate closed and the inactivation gate open. Um, and so with the activation gate closed, sodium, even though it would move into the cell, because it's the Nernst potential would indicate that it would move into the cell, it can't move in because it's blocked. Once there's a stimulus, either from a neighboring cell, neighboring neuron, or from an electrode stimulus, the membrane potential rises a bit due to that injection of current, of charge, and that's enough for the activation gate to open. So you can see it's almost like a throat opening. And in that case, when that happens, the sodium ions are free to flow through. And as they flow through, they increase the potential. Okay, they increase the potential up to a certain point, at which point the inactivation gate, the other gate, is programmed or is designed to close at a potential of around plus 10 millivolts. So the remaining sodium flows flows out into the cell, and the peak potential reached is about plus 20 or plus 30 millivolts. But then, even though the activation gate is still open, because the inactivation gate is closed, no more sodium can flow in. Once that happens, well, it's a separate story, which I'll show in a second. The potassium is free to start leaving, or as the potassium leaves, there's no sodium flowing in, and so the potential can return back here. So just looking at that again, at this point, at position 2, that's when the sodium activation gate opens and the sodium floods in. And position 3 is where the inactivation gate closes, and just a little bit of sodium flows in after that, just the remaining sodium which was present in the channel flows in, and then after the potassium flows out, we have the sodium gate, the activation gate closing, because we move below this position of minus 50 millivolts, where it's first activated, where it first opens. And then there's this period called the refractory period, and that occurs because the even if a stimulus came along to stimulate the cell to the ion channel to a higher potential as before, the inactivation gate takes time to reopen. Okay, so during this refractory period here, and there's a recovery period where the cell cannot fire. Okay. All right, so both the activation gate and the inactivation gate play a role in the flow of sodium into the cell. The sodium stops, and the sodium then is cut off. And then at the end, because the inactivation gate is still closed, there's a period before it opens again until the neuron is ready to fire and respond to a stimulus again. Okay, so let's look at the potassium gate next, just to see how the mechanism might work. In the potassium channel, there's just activation. There's no inactivation. There's no little. There's no two types of gates. So how this would work is, here we have the outside and the inside of the cell, and normally the inside of the cell is negatively charged with respect to the outside of the cell. And so there are two charged proteins in the gate, in the potassium gate, and those two charged proteins are drawn by the negative charge, net negative charge inside the cell to pull together and close the gate. However, if once the sodium has flowed in through other sodium channels, the inside of the cell becomes positive with respect to the outside, and those positive charges repel these proteins, and the negative charges outside attract them, and that mechanically opens the potassium channel, and the potassium can flow out during the repolarization stage. Okay, so that's kind of a mechanism for how one of these channels can work physically in terms of electrical forces. All right, next we'll look at a circuit model of the axon membrane, and we'll concentrate first on the sodium channels. So we modeled the circuit membrane as a capacitor with charge separated on one side and on the other side, negative charge on the inside and positive charge on the outside typically. And then the channels, the sodium channel and the potassium channel, and then this load channel, which includes the effect of other ions, are modeled as wires with a battery with an effective potential, which would drive the ion across the cell, and a resistance, or what we use as a conductivity, G. And G is just, conductivity is just the reciprocal of the resistance. Okay, so there's three types of channels, so there's three wires, each with their own effective driving potential, with the ability to change the charge on either side of the cell membrane. So at a given membrane potential, so let's say we've fixed the membrane potential, the sodium current would be the effective sodium driving potential over the resistance of the sodium channel. And again, we normally in working with channels, we just for convenience, we write 1 over R is G, so we work in terms of conductivities. So we write this as conductivity of sodium times the effective potential of sodium. Now, what's the effective potential of sodium? Well, it's not just the membrane potential, it's equal to the Nernst potential of sodium minus the membrane potential, okay? Because with the Nernst potential equal to the membrane potential, there's no net tendency for ions to flow, okay? It's only when the Nernst potential differs from the membrane potential that there's a tendency for ions to flow in or flow out. And current will flow in the direction to tend to bring the Nernst potential equal to the membrane potential. And we abbreviate the Nernst potential as just for sodium, instead of writing Nernst, we just write it as V and A, understanding that means the Nernst potential. And the sodium potential, the membrane potential, we just write as V. Okay? Now, we know from the action potential that the membrane potential doesn't stay constant. And so, in fact, the conductivity, the conductivity of the sodium channel depends on the voltage, because as we saw, the activation occurs at a certain voltage and inactivation at another voltage, membrane potential. And so the conductivity has to be modeled as a function of the membrane potential. So we have our overall equation then is that the current flowing in a given channel is equal to the conductivity, which depends on the membrane potential through the inactivation and activation gates, times the effective potential, which is the Nernst potential minus the voltage, or voltage, that meaning the membrane potential. Okay, so let's look at the equations for the full electric circuit model. They're just a generalization, including all three of sodium and potassium and the rest of the ions grouped together as L. So this is just a little illustration showing that the membrane is modeled as a capacitor separating charge on either side, that the channels are modeled as resistors, or with conductivity equal to 1 over R, or resistance equal to 1 over the conductivity, and that the effective potential here is equal to the Nernst potential minus the membrane potential. Okay, so this is just kind of a visual. And so we have the circuit diagram from the last slide reproduced here. The total current that's flowing into the cell will just be this current from potassium plus the current from sodium plus the current from the other ions. That current can be related to the capacitance by noting that the current is the rate of change of charge with respect to time, or dq dt, where q would be the charge, say the positive charge on the outside of the cell. And then, since for a capacitor q is equal to CV and the capacitance is constant, this becomes C times dV dt, where V is the membrane potential. So combining these, first, we have as in the case of sodium, we have the current for which is dependent on the membrane potential and on time, is equal to the effective potential of potassium, the Nernst potential minus the membrane potential, times the conductivity, and the conductivity of potassium depends, again, on the membrane potential because the gates open and close. As we saw in the previous slide, where the potassium channel opened and closed depending on which side was of the membrane was positive. And then this reproduces our equation from the last slide. Again, the sodium current depends on the effective potential for sodium times the voltage-dependent conductivity for sodium. And that's because of the inactivation and activation gates, which we looked at earlier. And then also the rest of the ions have a similar form. So then we can say that I total, which is C times dV dt, as we established before, where V is the membrane potential, would be IK plus INA plus IL, and we substitute our IK, INA, and IL in here. So here then we have a differential equation for the membrane potential. That's our main variable that we're trying to solve for. What we're missing here is how the expressions for how the conductances depend on the membrane potential. We know they depend in principle, but we don't have any mathematical form for that. And that's where the Hodgkin-Huxley model is going to come in our following class. So just to summarize, we've just looked and we have a circuit model of the axon membrane with the membrane acting as a capacitor and the ion channels as wires with resistances R expressed as conductances, which is the reciprocal of the resistance. So we have three, and then in that model we have effective potentials given by the Nernst potential minus the membrane potential, okay? Which, because, again, just to reiterate, unless the membrane potential is different from the Nernst potential, there'll be no tendency for ions to flow. And then the key point is that the conductances are not constant, but they're voltage dependent, which allows the timing of the opening and closing of the ion gates, the opening of the sodium activation gate, the closing of the inactivation gate occurring here, and then down here the closing of the activation gate of sodium, here the opening of the activation gate of potassium, and down here the closing of the activation gate of potassium, and eventually the opening of the inactivation gate of sodium, allowing the neuron to react again. So Hodgkin-Huxley, which we'll look at in a second, the main idea will be to model the conductances G in terms of the opening and closing of these ion gates. So to get more explicit models for these conductances so that we can have a full equation and integrate and find this action potential. Okay, I hope you found this useful and interesting, and I will see you in class.